All right, guys, 11.5, we are talking about volume here in the next couple sections. 11.5 specifically deals with volume of prisms and cylinders, very, very similar. There's a lot of stuff that goes into it. It's not simply finding the volume of it. That's kind of the easier part of all this is just basic finding the volume. So we're going to look at a little bit more. First thing we're looking at is Cavalari's principle. In Cavalari's principle, and you see the picture of it here. This is Cavalari's principle. Says that if you have the volume of a prism and then you slant it, it's going to have the same volume, right? And I usually show this with a stack of paper where I have a stack of paper. I'm like, all right, this is a rectangular prism. It's got a volume. And then I kind of shift the papers over a little bit so it looks more like this one, right? And I shift them. I say, did this lose any volume, or does it still take up the same amount of space? And of course, it still takes up the same amount of space. That is Cavalari's principle. The reason why that works is why our volume is going to be the same no matter what. And our volume for a prism is simply base area times height. Base area times height. You see it right there. Volume equals base area is the capital B, and then H is the height. Remember, height has to be perpendicular, right? Height is perpendicular here. This is not the height, okay? The height is perpendicular. So if it's straight up and down, great. If it's slanted, right? If it's on a slant, then we got to find that straight up and down, which means you might have to do some calculations, some Pythagorean theorem to find that actual height. Okay, and there's a difference between that height going up and down and this. We're going to deal with this in the next section. That's called slant height in a pyramid or a cone. We're dealing with actual height here. Okay, so pretty straightforward. You got to find the area of the base and then multiply it by the height. Here you've got a triangle. It's a right triangle. It's a 3, 4, 5 triangle. We don't need to know the 5. But we know it's 3 and 4. You can find the area of that triangle and simply times it by 2, right? Here you've got a trapezoid. You've got 14 for the long side, 6 for the short base of the trapezoid. And if you recall, area of a trapezoid is the average of the bases times the height. So for this problem, we would take the average of 14 and 6, which is 10, and then times the height, which is 3. So that would give me a base area of 30. Okay, base area of 30, that's the area of the base, and then we got to times it by the height of the prism. So then that would be 150. Just keep in mind there are two different heights that we're talking about here. You got the height of the prism, which is 5, but you got the height of the trapezoid, which is 3. So just make sure you understand which height you're dealing with as you go through there. Cylinder is the same exact thing. You see it's the same exact formula, same exact equation. Volume equals base area times height. The difference is we can get a little more specific because we know that base is a circle in a cylinder. We can not just say base area, we can say pi r squared because that makes it a little more specific there. So that's why you see that a little bit different. It is the same thing, area of the base times the height. We are using pi, right? Remember, sometimes it asks you for in terms of pi. In terms of pi or exact answers would look something like that, where you just have a pi in there. And then if they ask us to round, then we would type it in the calculator using the pi key to get that rounded answer. All right, moving on from that density, they talk about density here. As long as you know this formula, density is equal to mass divided by volume, then you should be fine on this. They're going to give you 2 of the 3, and you have to be able to solve for the third, is basically what they're talking about. Volume, of course, is what we're talking about. It's going to be a prism or a cylinder. Mass, they would either tell you, and density, they would tell you, or you would just divide mass by volume. The only thing you got to be aware of is sometimes you're going to have to do some converting, right? So here they're giving us the calculations, or rather the side lengths in inches, but they're telling us the density is grams per cubic centimeter. So they're dealing with centimeters. So we would have to change all of those inches into centimeters. Luckily, they give us that conversion right there. 1 inch is equal to 2.54 centimeters. That's one that, maybe you should learn. That's one that I know off the top of my head, inches to centimeters, just because I've used it a few times. But it's helpful in case you're ever doing some calculating there. Right, we would find the volume of that. So the density 19.3 equals mass divided by whatever the volume is. We can multiply, we can solve it. The only real difficult part about that is converting to the centimeters. Moving on, like I said, there's a lot of stuff in this. Modeling, just sometimes they're going to give you that figure, they're going to give you the volume, you're going to have to solve for one. So set up your equation, right? You got base area times height, so 24 times the height equals 72. We know the height has to be 3. So that's what they're looking at example 4. Example 5, same idea. They gave us the volume. This time they gave us the height. They want the base area. So we got the base area has to be 6. And then it says give a possible length and width. Well, it could be 3 by 2. It could be 2 by 3. It could be 1 by 6, right? I'm sure there are other ones out there. And you're going to see some problems in the homework like that where it's which ones of these could it possibly be for the base area there. Moving on, similar solids. This takes what we dealt with in terms of area and similar figures, and it takes us the next step. If we recall, I know it's been a while, but if we recall, K is scale factor, right? K is scale factor. And so we said back in the day, if we had a figure like this where we doubled every side, let's say we went from 3 to 6, we doubled every side, that told us that K was the scale factor. And we said that perimeter had the same ratio. The perimeter was going to be twice as long. But we said the area was always K squared. That was the ratio. So in this case, our area would be 4 times bigger, not 2 times bigger, because it's 2 squared. Well, volume, since it's a 3-dimensional measurement, is going to be that scale factor cubed now. So if everything is twice as big, right, a scale factor of 2, my volume is going to be 8 times bigger, because that is now 2 to the 3rd times bigger. It's now 8 times bigger. So you really got to think back to what we did with area, because we did this quite a bit, and I think we got it pretty good. You're going to see those same types of problems, just now instead of having to square that scale factor, we are cubing that scale factor to be able to get our new volume or our new side length or whatever it is. And you see that example here, right? And it's exactly what we just talked about. Our scale factor is 2. We have to cube it. So it's 2 to the 3rd times bigger. So it's 8 times bigger. So that 45 pi times 8 would give us 360 pi. And we can just leave it right there as 360 pi. That's okay. We don't need to, unless they tell us, we don't need to round it. Right? So we can just leave it like that. So again, scale factor is K. Area, we square the scale factor. Volume, we cube the scale factor. So the scale factor to the 3rd power, as you see here. Make sure we're good on that. Composite figures where you've got 2 things added together, you got holes and things. We should be okay on that. You really got to pay attention to what information do we have. Am I adding things together or am I subtracting 2 things apart? In this case, you got a whole big figure and then you got 2 things dug out of there or drilled out. So we are subtracting in this case. You see area of the large rectangle minus the areas of the small. That's giving us that base area. So really this right here is just finding the capital B, which is base area. Then once we have that, then we can times it by the height of the prism, which is 0.66. You could do that, or you could find volume of the whole thing and then subtract the volume of the 2 smaller ones. It's going to work either way the same. Okay, but you might want to look at that. Right? You might see a problem or 2 like that. Like if we see this triangle one down at the bottom, if we are going to do this, what I would do is I would find the area of the whole big thing. Um, and again, you might have to, well, it says it's equilateral, so to find the area, you're going to cut it in half. It's going to be a 30, 60, 90. So if this whole thing is 10, that means that whole thing is 10. Let me redraw it. Here's my triangle. If we know this is 10 and it's a 30, 60, 90, that means we cut it in half. That's a 5. That means my height is 5 root 3. So if I'm finding the area of that whole triangle, it's going to be 1/2 base times height. Right, that's going to give me the area of that triangle. Then I would subtract the area of the square. So I would subtract 9 from whatever that is. And then I would times it by the height of the prism. And the height of the prism is 6. That's how we would get the volume of the whole thing there. Okay, so a lot of things to look at. 7 examples, kind of flew through some of it, but take a look at the book, read through it, watch the videos on there. I think we'll be good to go on it. Really, I think the hardest thing is example 6, so you might want to take some time and double check, just make sure you understand that.